Hello children, we'll continue with this exercise of finding equivalent resistance. I think you have done till 17 as homework. I had given till 17 as homework. Now we are going to do 18th. Okay, this is slightly different. So they have given a circuit like this: A, B, C and D. 2 ohm, 2 ohm, 2 ohm and 2 ohm. Okay, and the question is, you have to find the equivalent resistance between equivalent or total resistance between A and B and then A and C. Okay, between A and B and A and C. Now this kind of circuits, it's very difficult to decide which is series and which is parallel. Yeah, it looks as if these two are parallel and these two are parallel. No, it's not like that. Okay, you can't just decide by looking at it. Okay, so that's why what we have to do is, now if they are asking you to find across AB, across A and B, means what you have to do, you have to assume that there is a battery here. A and B, this is A and B, you are asked to find across A and B, so you have to assume that there is a battery here. Now if there is a battery here, the current I will come here. Now one way to decide series parallel is just by looking at it, like this series and like this parallel. One next to the other is series and one below the other is parallel. Now every time it won't be, you can't see it directly, it will be like this box kind of a thing, then it is very difficult to decide. So there is another property that you can remember. In case of series circuit, if I is the current coming, same current will be going through all resistors. This is R1, R2 and R3. Same current will be going through all three resistors. But in parallel, what will happen? If I is the current coming, the current will divide, because it's like it's splitting into three parts. It's splitting into three parts. So the current will divide as I1, I2, I3. So this is another way of deciding series and parallel. If the current is going to remain the same, if the same current is going to go in a path, then you say they are in series. If the current divides, means wherever there is a junction like this and there is a division, there is a splitting, then we say they are parallel. Okay, we are going to use this concept here to decide which are all in series and which are all in parallel. Now across A and B means when you look from this side, or you assume there is a battery from this side, current I is going to enter here. Now here there is a junction, means there is a splitting, and so current is going to divide as I1 and I2. So that means these two are parallel. These two are parallel. But don't start solving it immediately. You have to see the entire path. Okay, see the entire path. Now this current I1 that is going here, if you see, the same current will go here also, because there is no another path. There is no splitting here. There is no branching here. So the same current, whatever was going here, will go here also. And the same current, whatever comes here, the same current will come here also. So what can I conclude? From this point till this point, now after this it will change. So from this point to this point, same current is going. So all these three are in series. Okay, all these three are in series. Okay, so that's my first conclusion. Now if they are in series, first you solve that. Don't first solve the parallel. See the complete path and then start solving from behind. It's like this is parallel to the complete thing. So first you solve for R series. So 2 plus 2 plus 2, that is 6 ohm. Now how will your circuit become? Now all those three resistors, you can replace it by a single 6 ohm resistor, and then you have your this 2 ohm resistor and then your battery here. Now how are they both? Parallel. So 1 by Rp is equal to 1 by 6 plus 1 by 2, 6, and 1 plus 3, that is 4 by 6, or Rp will be 6 by 4, 3 by 2, 1.5 ohm. Okay, I can write it as RAB. because they've asked specifically across AB, you can write that as RAB. So RAB is 1.5 ohm. Now we'll go to the B part. B part, they've asked you to find across A and C. So for this, what you have to do is the same, you'll take this circuit, again you redraw it. So this is your A, B, C and D. 2 ohm, 2 ohm, 2 ohm and 2 ohm. Now you have to find across A and C. So what you have to do, you have to assume that there is a battery across A and C. Okay, you have to assume that there is a battery across A and C. So current will be coming from here. Okay, from the battery current will come, and what will happen here, they are going to divide, and this will become I1, this will become I2. That means these two are parallel. These two are parallel. As I told you before, don't immediately start solving for the parallel thing. You see the entire path. You see the entire path, then you can decide. Now, the current I1 that is going here, the same current will be going here. There is no branch here. There is just a single path. So the same current would have gone here also. So this will also current through this also is I1. Same here. I2, the current I2 which went here, the same current will be going through this also. So what is my conclusion? These two are in series and these two are in series. So what will happen to my circuit? So this 2 plus 2, so RS is 2 plus 2, that is 4 ohm. Okay, both. So these 2 and 2, I can combine it and again write one 4 ohm resistor. Now how do they look? They are parallel. It's like two 4 ohm resistors in parallel. So 1 by Rp is equal to 1 by 4 plus 1 by 4. And that will be 2 by 4, or Rp is equal to 4 by 2, that is 2 ohm, or RAC. You're finding the resistance across AC. So write it as RAC is equal to 2 ohm. See, the values are different. Across A and B, the resistance will be different. If you put a battery here, the equivalent resistance is different. If you put a battery across this, then the equivalent resistance will be different. So that is how you get two different answers. Okay, children. So for circuits where you are not able to, by looking at it, you are not able to make series and parallel, this is the best way to decide which are all in series and which are all in parallel. Okay, now this one we will be doing as homework. Okay, 5 resistors each of 3 ohm are connected as shown. Calculate the resistance between P and Q. So you have to find the resistance between P and Q and then between X and Y. Now when you are finding resistance between P and Q, what you will consider? You will consider that there is a battery here. So now what will happen, these two resistors, is you should not consider when you are finding across between P and Q. When you're finding a resistance between P and Q, you should not consider them, because one end is fixed, the other end is hanging in the air. There is nothing here. So you just omit it. You just leave it. You just only have to consider these 3 resistors. Okay. So what you will decide, these two are in series, 3 plus 3 is 6, then in parallel with this 3. But on the other hand, when you are doing, so the across XY, then you will assume that there is a battery across XY. That time you have to consider this and this. Okay. For B part, when you're finding across X and Y, consider these two. Okay. So this one you would have already found. Then all the 3 will be in series. You have to add it. Hope it is clear. So 19th one you will be doing as homework. Now we'll come to the C part. Theory, okay, C part of this chapter. Electromotive force, terminal voltage, internal resistance of a cell. So these are new terms, electromotive force, terminal voltage and internal resistance of a cell. So let's try to understand these terms. Now, let's take a battery. Okay, and this is a switch, and then there is a bulb. Okay, so bulb is the load and this battery is used to light this bulb, or basically the battery will give some current when you connect this bulb to the battery, and if the key is closed, okay, if it is open, no current will flow, so the bulb will not glow. So when I switch it on or basically close the key, then the bulb is going to glow, okay, because current will be flowing here. Now when the key is open, means when no current is, so now what I have done is I'm going to connect a voltmeter across this. I'm going to connect a voltmeter across this battery. You know, voltmeter measures voltage, and we also always have to put it in parallel. I'm going to measure the voltage of this battery. Okay, assume that it's a 2-volt battery. It's a 2-volt battery. Now in this case, when key is open, that is no current is flowing. In case when key is open and when no current is flowing, the voltmeter will also be showing 2 volt. In the voltmeter, the reading will be 2 volt. Okay, now you close the key. Key is closed and current starts flowing. Current is flowing. Okay, so the same circuit, but the key is closed. That means like this, and then you have your bulb here, and then you have your voltmeter here, and K and bulb B. Now in this case, when the key is closed and when current started flowing, so current I started flowing, and you know this is a 2-volt battery. In this case, the voltmeter will not show 2 volt. It might be showing say 1.8 volt, less than 2 volt. It will be showing a voltage which is less than the 2 volt. Okay. Now this voltage is called EMF. Okay, this one is called EMF, and this one is called terminal voltage. In the sense, when current is not flowing in the circuit, whatever is the potential difference. Now what is voltmeter actually measuring? The potential difference between these two terminals. So whatever is the potential difference across these terminals of the battery, that is EMF, electromotive force. On the other hand, when the key is closed, when current is actually flowing, whatever is the potential difference across this battery, that is called terminal voltage. That is called terminal voltage, and terminal voltage will always be less than EMF. Terminal voltage we represented by capital V. EMF we represented by capital E. V will always be less than E. Now, what has happened? Why is, while the current is flowing, why is it only showing 1.8 volt? It is not giving 2 volt, it is only giving 1.8 volt. Now where did this 0.2 volt go? Okay, now that is called potential drop. So first term is EMF, second term is terminal voltage, and then the third term is called potential drop. So what has happened? The potential has dropped or reduced. Okay, that's called potential drop, and small v, and it will be equal to E minus V. That is 2 minus 1.8, that is 0.2 volts. This is called potential drop. In the sense, this much got wasted. It is not usefully used. Where did it go? I'll tell you. Okay, children. So we have seen 3 terms: electromotive force, terminal voltage, and potential drop. Okay. So see these definitions. This is the definition of EMF. When no current is drawn from a cell, that is, when cell is an open circuit, the potential difference between the terminals of the cell is called electromotive force. Okay, it is represented as capital E. You can strike off this definition. Okay, it's a little complicated one. Then come to terminal voltage definition, this one. When current is drawn from the cell, okay, that is when the cell is in closed circuit, means when the key is closed. Here the key is open, here the key is closed. So when the cell is in a closed circuit, potential difference between the electrodes of the cell is called terminal voltage, and it is represented by capital V. It is represented by capital V. Okay, again you can cut off this. This is another definition. It's enough if you study this definition. Then comes the third term, potential drop or voltage drop. You can even say voltage drop, that is small v. Okay, capital E, capital V, and this is small e. So the terminal voltage V is less than its EMF by the amount of energy spent in the flow of charge through the electrolyte, or you can say potential drop or voltage drop is the value by which the terminal voltage is less than the EMF. It is the value by which terminal voltage is less than the EMF. Okay, so this difference between E and V is called potential drop. Okay, so 3 definitions we have seen so far. Now what relationship can I get from of these 3? EMF is equal to capital V plus small v. EMF is equal to terminal voltage plus potential drop. So E is equal to V plus small v, or V is equal to E minus small v. This is the relationship. Now come to the next page. You have differences between EMF and terminal voltage. First point is the definition. They have given the other definition, which is little difficult. So you can, whatever definition you're studying here, you write here as the first point. So I've written write the other definition. Okay. Second point, EMF is the characteristic of a cell. It does not depend on the amount of current drawn from the cell. EMF, if it is a battery of 2 volt, its EMF will always be 2 volt. You connect one bulb here, you connect 2 bulbs here, you connect 3 bulbs here, doesn't make a difference because this key is open, no current is anyway flowing. So EMF will always be constant. Whereas in this case, if I connect another bulb here, so what will happen? The current will reduced because 2 loads are there, so this current will decrease. Okay, its terminal voltage was 1.8 before. Now when I put one more load, maybe it would have, its terminal voltage would have become 1.6 volts. Okay, because the current has decreased and terminal voltage will also decrease further. So that is why this point says it depends on the amount of current drawn from the cell, and the amount of current drawn from the cell will depend on the number of resistors or number of load that is here. So that is why this is always constant, this keeps changing. Okay, this is equal to terminal voltage when cell is not in use. Okay, and when cell is in use, EMF is always greater than, or terminal voltage is always less than EMF. Okay, now comes the main concept. Why is this difference? Now why do we have 2 different voltages? One is called EMF, another one is what happened to these 0.2 volts? Where did it get wasted? Now here comes the concept called internal resistance of a cell. Internal resistance of a cell. So this battery, which is considered to be the source of current, itself is offering some resistance. Why? Because you know a cell basically has some electrolyte. Okay, there are 2 electrodes. One is anode, other one is cathode, and there is an electrolyte here, and then it behaves like a cellular battery. Now these electrodes and electrolytes also will offer some resistance. These electrodes and electrolytes will offer some resistance to the flow of current. Now so far the resistance we talked about is due to this, the wire, or due to this load. But now we are coming to a conclusion that this battery itself offers some resistance to the current flowing inside. That's the reason why when current actually started flowing, it offered resistance, and that's why instead of 2 volt, it was giving only 1.8 volt. So that is due to this term called internal resistance of a cell, that is due to the electrodes and electrolytes in a battery. This is represented by small r. Now define the definition of internal resistance of a cell. The resistance offered by the electrolyte inside the cell to the flow of current is called as internal resistance of a cell. Okay, it's because of this internal resistance only some voltage got wasted in overcoming that resistance, and that is called potential drop or voltage drop. Okay, small v. So internal resistance is small r, and small v is equal to I into small r. Okay, this internal resistance, because of this there will be some voltage drop, that is called the potential drop or voltage drop. So small v is equal to I into small r. So children, you have to be careful. You have E, okay, only one, but you have capital V, small v. In a circuit you'll have all these things, and then you'll have capital R and small r. This is EMF, this is terminal voltage, this is potential drop or voltage drop, this is external resistor. The sense, the resistance of these things are, this is considered as external resistor, and whatever is the resistance offered by this battery, you have to, hereafter you'll be putting one small resistor near the battery itself. That will become small r, that is internal resistor. So capital R always represents external resistance and small r represents internal resistance. Internal resistance. Okay children, so now you have to be careful. When I say V, it is big, capital V or small v. When I say R, capital R or small r, both will represent different things. Okay, so as I told you, if I have to represent in a circuit, okay, now in the numericals sometimes they will say a battery has its EMF is equal to terminal voltage. That is very rare. In the sense, a battery with internal resistance 0, which is very, very rare. But some numericals, for theory sake, you can take anything, right? So, but if they give internal resistance also, then what you have to do is, along with the battery, so you'll write EMF here, and along next to the battery itself, you'll draw one small resistor, that is internal resistor. This together is considered as your battery now. These two together considered as a battery. And then R is your external resistor. It can be the resistance of a bulb or a fan or whatever it is. That is resistance is capital R. And I is the current going. Okay. So according to Ohm's law, I is equal to V by R. Now, in this case, we are not having internal resistance. We are just having a battery whose EMF, terminal voltage, everything is the same. Okay. And then there is just one resistor R connected to it. In that case, current I, you will just write V by R. If there was no internal resistance, then current's formula is V by R, which you saw in the previous part. Now, suppose if there is an internal resistance, okay, practically in most cases there will be internal resistance. Now, current will become, okay, in this case, now this is like two resistances in series. So, R series, if I do capital R plus small r. So, what will happen to my current? This is the voltage, that is the source. So, E by R plus small r. Okay, so when I consider internal resistance, current formula will be not just V by R. This is when no internal resistance is there. So when internal resistance is there, then the current formula will become E upon capital R plus small r. This is EMF, this is external resistance, and this is the internal resistance. I hope you're clear with this, children. Okay, so E minus V, okay, is equal to small v, which is also equal to IR, or E is equal to V plus I into small r. This is also another formula. Okay, and remember, capital V is I into capital R and small v is I into small r. Terminal voltage is current into external resistor, external resistance. Voltage drop is current into internal resistance. Okay, these two also you should remember. Then E is equal to V plus I into small r. This is also another expression. Okay, so these are expressions, and finally E is equal to V plus I into R. And then finally we have factors affecting internal resistance of a cell. So there are four factors that are going to affect One is surface area of electrodes, that will be inversely proportional. Distance between electrodes, directly proportional. Nature and concentration of electrolyte, again directly proportional. More the concentration of electrolyte, more will be the internal resistance. And temperature of electrolyte, inversely proportional. The explanation we'll see later. Right now you just mark it like this: inverse, direct, direct, and inverse. So these are the four factors affecting internal resistance. Okay, so I'll be giving some homework, some extra numericals based on this combination of resistors. Please solve them and send it to me. Thank you, children.